Hi everybody, I'm Paul Rothrock, a solution engineer here at pgEdge. Because logical replication like pgEdge is eventually consistent, this opens up the possibility of data divergence across the cluster. For example, if two transactions are performed at the same time that update the same record but go to different servers in the cluster, which one should be the source of truth? Or if network connectivity is interrupted during an insert, how do you handle updating that record on a server where the insert didn't happen? This video will show you how pgEdge can handle these situations as they happen and how it can repair them after the fact if necessary. To start, let's explore how pgEdge manages conflicts. By default, pgEdge uses a last commit wins algorithm for conflicts. That means if a write transaction comes in two servers for the same row, the one that is committed last will be applied across the cluster. Also, the resolution of this conflict can be stored in the spock.resolutions table to provide an audit trail. However, this isn't always the best way to handle every conflict. For example, let's say your application is tracking account balances or inventory numbers, where every commit must be applied in order to maintain accuracy. pgEdge gets around this with its exclusive conflict-free delta apply columns. This allows you to specify certain columns in your schema to apply all updates, not just the last write. Let's look at an example. Here we have an account with a $1,000 balance and two conflicting transactions come in, one adding $10 and another deducting $20. With standard last commit wins, only one of the transactions will be logged, causing the balance to be incorrect. But with delta apply, all transactions are applied in order, so we'll add $10 and deduct $20, resulting in the correct account balance, $990. As with last write wins conflicts, these can also be logged to the spock.resolutions table for auditing. Now let's look at how conflicts can happen and what they look like in pgEdge. Each of these windows are connected to one node in a two-node cluster. I'll start a transaction to update a field on the database on the first node. Then on the second node, I'll start another transaction, update it to a different value. Then commit the transactions one after the other. Then when we select value on both servers, we can see the last transaction committed determines the value. And when we query the spock.resolutions table, we can see the resolution logged there. But there are some conflicts that can't be resolved by Spock, which we call exceptions. These can be caused by things like network or hardware failures and come in two flavors: missing or duplicate primary keys and missed DDL statements. A missing primary key exception happens when an insert is not replicated and subsequent updates for that record fail. A duplicate primary key is like the former, but where two records have the same primary key. This exception can be prevented by using snowflake sequences, which will ensure that the keys are unique for every record. Finally, a missed DDL statement exception happens when a table or column is not available on a server because the schemas are different. This sort of exception can be mitigated by enabling pgEdge's AutoDDL feature, which will replicate those schema changes across the cluster. pgEdge keeps a record of these exceptions in the spock.exceptions table, showing the operation it was attempting, the local data, and the remote changes that could not be applied. Now let's see what it looks like in pgEdge when an exception happens. As before, I'm connecting to one pgEdge node on the left and a second on the right. First, I'll use Spock's repair mode to insert a value into just one of the nodes. As you can see, the new record doesn't exist on the second node. So when we attempt to update that record on the first node, it will generate an exception on the second, which we can see in the Spock.exceptions table. To fix this, we enter repair mode on the second node and insert the record, and then we can update it without a problem. However, with a lot of exceptions, this can take a long time. That's why pgEdge created ACE, the Active Consistency Engine. This is a tool that runs outside of the pgEdge server to monitor data consistency and repair any drift. ACE can be run manually, or it can be run at regular intervals to report on and perform repairs. ACE is optimized to review millions of rows efficiently by implementing Merkle trees and was recently rewritten in Golang to avoid dependency issues. It can analyze and repair a single table, a full schema, or the Spock settings across your cluster. Let's take a look at how you can use ACE to analyze and fix drift. As you can see, I have the same servers on screen and they're out of sync. First, I'll run a table diff on that table, which will find the differences and generates a JSON diff file containing the details needed for ACE to do the table repair. The next step is to do a dry run of the table repair, using node 0 as the source of truth and passing the generated diff file into it. Doing a dry run is the best practice so you can see what operations will be performed. Once you're comfortable with the changes that will be made, run the table repair again without the dry run option, and it'll perform the operations across the entire cluster. Once that's complete, we can query the second server and see that the records match. Now that you know how pgEdge manages conflicts and repairs data, you'll see why so many organizations trust it with mission-critical applications. Not only will it automatically handle conflicts in two different ways, ACE can be used to quickly and easily make any necessary repairs. Leave a like if you learned something, and be sure to subscribe for more tips and tricks. Thanks for watching.